Can you hear me now?
Yeah.
Okay, start time 9:55, and then end time, let's see, hopefully 11 o'clock. Okay, first one is create drawer. So we have 6 drawer that we need to create. Liquid pressure, atmospheric pressure, gas pressure, Pascal principle, Archimedes principle, and Bernoulli's. So if you
Yeah.
realize, there are actually 2 categories: the type of pressures
Pressures
and
and the
3 type
principles.
of principles. Yes. Now, I'll assume that you are having zero knowledge. So I'll start from zero. So the story that I created for us to remember this drawer easier is liquid evaporate into gas, right? But I changed my evaporate to advaporate because it is representing the liquid pressure, atmospheric pressure, and gas pressure, right? Because liquid, if you change to gas, the process is called evaporation. So I changed the name. I changed the spelling from evaporation to evaporation. Then the second part is about the principle. Papa, which is Pascal. Achi, sneeze. At I put baby, or you can put Bernard or whichever friends that you want to put it as in this drawer or this story. Then you can put it. It can be
Okay.
Bernard. It can be baby. It can be Benedict. It can be Benny, right?
Benny.
Yes. So you want Benny?
Yeah.
Okay. You know somebody, Benny?
Not really, but it's catchy.
Okay. So liquid evaporate into gas. Papa achi at Benny.
Hmm.
Right. So that is step number 1. So we have done step number 1. Let's go to step number 2. I'll extend this. So remember the drawer?
Yeah.
Can you tell me what's the drawer?
As in like the drawers from earlier.
No, this one.
Huh?
Yeah, there's 6 drawers.
Uh,
Yes, what's
like
the story?
the oh, you mean like liquid evaporate into gas, which is the pressure in liquid. Add for the atmosphere, gas for the gas pressure, and then Papa Achi at Veni,
Yes. Papa is Pascal.
Pascal, and then
Achi is
Achi is the Archimedes, and then
Yes,
Veni is Bernoulli.
exactly. So you already remember the 6 drawer now. Now we have to fill up the drawers with the informations. So before that, let's read this quickly. Even if you do not understand fully, it's fine, and that's normal. Let's do that now for 2 minutes.
Okay.
Okay? Okay, let me bold these 6 drawers. Okay, well, I'm bolding. Can you tell me the 6 drawers?
Okay. Liquid evaporate into gas. This part is for the pressures. Liquid is for pressure in liquid. Evaporate is for the atmospheric pressure, and then into gas is for the gas pressure. The other part is for the principles. There's Papa Achi at Veni. Papa is for Pascal principle. Archie is for Archimedes principle, and then Benny is for Bernoulli's principle.
Okay, now let's read the summary and tell yourself which drawer. Let's start from here.
Principles and factors. SPM. Okay.
Okay, what are the key things over here is there are two parts over here. One is the formula, pressure with the depth of the liquid, with the density of the liquid, with the accelerations. So this is the story that I created. Papa dive into a mercury and then pulled by gravity. What does it mean? It means that he dived into a mercury. Mercury means the density is different, and mercury is something very toxic, so it will create some emotions for you. And the gravity is the gravitational accelerations. I think this is standard 9.81 milli
Yeah.
per second. Yes. Then dive into the mercury means there's a depth that he has to dive into. So that is the pressure of the liquid, right? And then the second part over here is I intentionally did not put over here. So this is a new information. So this basically is telling you it is doesn't matter which container or the shape of the container, is the pressure is the same and it's in omnidirection, all directions.
All directions.
Yes. And uniform at the same depth. If it is different depth, of course it's different because you see that H is here, right? Okay, let's take this before we go to second drawer.
Okay.
Okay, it's just about applications. So I did not put over here, but I think you get the idea. You have to put some of these applications, not all of them, that make sense to you, to put inside your drawer. Especially this dam construction, empangan. This is very important. Okay, let's go to drawer number 2.
Okay.
Okay, this is talking about the atmospheric pressure that is on the Earth surface, right? Earth surface, if you are not at the Earth surface, if you are like 1,000 kilometer above the Earth, then your pressure is a bit different, not exactly the same, right? So
Like
that
on
is talking
moon.
about, yes, talking about the atmospheric pressure. Then of course there are some measurement, 14 and aneroid barometers, and depending on the accuracy that you want to use it and the application that you want to use it. So let's go through that before I tell you the story. Okay. Until let's say here.
All right.
Okay, let's continue. Then I'll tell you the story a bit more before we go to drawer 3.
Okay.
OK，这个 drawer 其实分成3部分了。第一个是讲关于什么是 atmospheric pressure， 然后第二部分是 unit of pressure， 然后第三部分是 the effect， 有2种了 ，effect 就是一个是 high altitude， 一个是 deep in the sea，
Deep
一个
sea.
是对，一个是爬山爬 Mount Kinabalu 或者是 Mount Everest， 第二个是潜水哦。So what I did is I created this story that is more related to 这个下面这2个，就是 effect， 因为上面这个好像没有什么很 interesting 的东西，就是这个760或者是这个100千，就是一个数字啦，没有什么很 interesting 的东西，所以我就用这2个去做 story， 我就讲爸爸他是吸 oxygen， 然后他在海里面呢，他在海上面，就是他在游泳的时候，他 floating 的时候，他 breathe oxygen，and then 他放屁跟肚跟肚，为什么跟肚呢？为什么 oxygen 呢？oxygen 就是讲你如果是 high altitude 的时候，你就会有less oxygen，and that is going to affect 这个 breathing 还有 metabolism rate because of a lower oxygen absorption。Right, then you have this impairment, cognitive function, and all these things. Then for 跟肚呢，跟肚放屁，那个我们的屁其实就是nitrogen， 是有一点 nitrogen 的那因素在里面，所以我就讲 OK， 爸爸在吸 oxygen， 然后就放屁在 ocean 那边，
在海
在海那边，所以这个就是在海的时候呢，你就会有这种他们叫这
nitrogen
个nitrogen
decompression sickness。
对，太多 nitrogen 了，right，所以就有这个 decompression sickness 啊，这样去 relate 这个东西，OK，就是这个 story，暂时就这两个 story，爸爸跳进 mercury 里面，然后给 gravity 拉下去，然后又是爸爸啦，然后就又吸breathe oxygen，然后又放屁，在踩里面啊，然后第三个时候比较简单，哎，就这个吧，
嗯，哦，哦，第三个比较短。
短更简单。
嗯，manometer。这个，OK。
OK，所以就是这个 nanometer、water nanometer、mercury nanometer，还有这个 formula。这个 PATM 就是 atmospheric pressure，然后这个 H 就是那个length 那个 height the difference of height on 这个 U shape glass。所以我怎样画这个 story 呢？就是比如说一个人啊，比如说是你啦，你在 blow 吹一个 pipe，那个 U shape 的 pipe。然后这个 U shape 的 pipe 里面呢有包含水跟 mercury。OK，这可能有点难想象啊，我直接跳过去给你看我画的东西这样有一个这样的 U
嗯
shape 的一个东西，一个 water 跟
嗯
mercury，然后你再吹它你在吹它，这个就代表它是gas pressure，然后你可以
嗯
算那个 gas pressure 的，其实就是你的 experiment 来的。我不知道怎么去 create 这个 story，这个 story 比较难 create。诶，在哪里了？三完了，二完了，三了，OK。诶，不是，
意思的
这个
Pascal
是
principle。
对第四第四也是很简单。第4的 formula 不简单，等一下你就简单了。现在暂时你第一次看的话不简单。
OK。
OK，这个其实讲到完最后就是讲hydraulic system。你有没
嗯
有想象 why we are able to brake the car by just pressing on the brake，
嗯
轻微的去 press on the brake 就可以整个一辆车是差不多整200-300 kg 的 不是整一两千 kg 的东西可以这么快速的去停下来，就是 they are using Pascal principle. Pascal principle, in other words, is force multiplications, right? You press, you just use a little bit of force on your foot to press on the brake, and it will able to stop the entire car, which is so heavy and having a big momentum, right? That is being done using the force multiplication, which is the Pascal principle, right? So how do I create this story? Is Papa is a strong man with force multiplier, so he has this superpower. He has this superpower. So this is representing the Pascal principle, how hydraulic system, right? Now maybe you do not understand the formula yet, but just bear in mind for now there is a formula with F with A. Then later with another steps you get it, you be able to understand it more. All right. Force is the F, A is the area. You need to know that by for now. Later you know it more. Right. Let's go to the Archie, the fifth drawer.
Archimedes principle.
Yep.
Okay.
Okay, let's finish this small part. Then we go to I'll tell the story.
So like all right.
Okay, Archimedes principle 在讲什么呢？其实你读这个 Archimedes principle state that an object which is partially or fully immersed in a fluid will experience a buoyant force equal to the weight of the liquid displaced. So 它就是讲船的原理了，right？为什么船可以浮？然后
buoyancy.
对 buoyancy，假设你现在有一个 water tank， 然后这 water tank 里面有一个fill up with water 到它那个最 top 的 level 的，差一点点就要那水就要 splash 出来了的。然后有一个小船在那边，然后如果你坐上去那个小船哦，如果那个小船没有沉呢，如果你是40公斤了，假设你是40公斤了，那些水会 splash 出来是吗？那
嗯
水 splash 出来的那些水哦，你拿去称啊，也是40公斤的这个就是 Archimedes principle。
嗯
OK，so 它就是讲 the weight of the fluid displaced 就是 equivalent to 那个 buoyant force。buoyant force 代表什么呢？代表你没有沉嘛，你就在那边，就因为有一个 buoyant force 在推你上去。
嗯
那个保安会推你上去，到你不会沉，是因为代表什么呢？代表你的40公斤上面下来的那40公斤，从下面水那个保安 force 推上去，也是要40公斤，你才会不会沉嘛，不然的话你就会沉了嘛，对吗？这样那个 buoyant force 它那个 force 是 equal to the weight of the fluid displaced，就是你是40公斤，那个水 displace 出来的那个水也是40公斤。这样如果是要很大量的fluid displace，当然海是没有的 displace 啊。不过如果是要 displace 的话，是不是要很多水才可以 displace 掉它那个船？因为它 design 它的船，它不是一支棍这样一支这样直接就沉下去了，它是 design 到它可以浮在那个在水面上的，因为它的那个 surface on the water 是很大的。你越大的话，你那个 buoyant force 就越大，这样你就更难闯，更难沉哦。就是 that's the concept，船就不要沉了嘛，船是不要沉
嗯
的。OK，
，OK，
这样这个 story 什么 story 呢？就是你也好，你爸爸也好，看你要不要用回你的爸爸啦。然后阿气，我用你是因为什么呢？因为我要放轩轩在这里。OK，你阿气一盆水那盆水呢就 splash 出来，然后中到轩轩的脸，
轩轩，
对吧？真的好笑是吗？所以这个就可以解释那个水 splash 出来中他脸，就是那个 splash 出来就刚我的那个40公斤那个东西，40公斤的水
嗯
啊。好，最后一个最后一个来你读一下。
嗯，Bernoulli's principle Benny，OK，
对，这个其实讲到完就是讲飞机的原理，飞机怎么快，怎么会
aerodynamic，
飞。 对 aerodynamic，这样你知道哦，这个这样我就不用再解释了。像那个 story 是什么呢？story 就是你跑到很快，然后你飞起来，这个就是那个 story。OK，
嗯，
来下一个 step four，好，我们 go to step four 了。step four 就是一样啊，我们读，然后什么 stop drawer，然后你就在读，看有没有新的 information。
嗯，
Okay，let's start with the question。这是第一个 drawer 对吗
啊，对，这个是第一个 drawer 的。
？OK，然后第一个 drawer 你看它的 keynotes 有这几个小东西了啊，这几个小
嗯
东西，然后你再看回去这个答案有没有新的东西你要放进去的，放进头脑里面的。
，OK，我
OK
是 right。嗯，
OK，number two，
哦，damn，这个也是第一个的。
嗯，
OK，
诶，没有有一点新 information 是吗？
啊，有一点都是讲的那个 dam 的，它的
对对对
structure。
，OK，好，next，OK，
这个是第二个 evaporate evaporate oxygen and conduct in ocean。嗯oxygen 那个 nitrogen。OK，
到完了，
还没有到那个 extreme C 的还没有。
可以。
OK，
Okay，number four，you're
这个是第三个，哎，对，第三个
right。
manometer gas pressure 的。 OK，
第五，
这个是对 Pascal principle
对哦，
multiplier 的。
没有错。你看你现在会不会更明白那个 formula？
OK，这个 Archimedes 这个 Archer ，OK，
好，第七，
还是 Archimedes，
先睡停。
嗯，OK，
最后一个 last one，
Bernoullis Benny，Newton's third law，
new information.
嗯
But Newton's third law is in force and motion.
之前有，
对，Chapter 1 from Form 4 and Chapter 8 from 5。
嗯 Okay.
Okay, before we go to step 5, let's try to remind ourselves what is the story about these 6 drawers. All right, the first story about the story about the first drawer is your
Papa dive
papa.
into Mercury, 然后 pulled by gravity.
Yes, and that is explaining this part, right? Then second drawer is about papa breathe oxygen and kentut
Oxygen,
in
然后 kentut
in
in
the ocean.
ocean.
What? Yeah, when he was floating in the ocean, and this is talking about the effect of atmospheric pressure for
pressure,
high
the
up in the
decompression
mountain.
sickness.
Yeah, and decompression signal in the inside in the sea, under the sea. Right. Then gas pressure. This one is
U
not
pipe.
so interesting, but okay, it does the job. You blow the U pipe and with water and mercury. Right. Then the next one.
Pascal principle 是 Papa's strong with the force multiplier for the hydraulic system.
Yes. Then the next one.
You are two. You seize the water and splash on Shen Shen face. Archimedes principle. Buoyant force.
Yes. Okay. The last one is you run fast and you fly.
Fly. Yeah, aerodynamic. Bernoulli's
Okay.
principle.
Right. So good. So let's start step 5.
Okay. Okay. Um, Alright.
第二个 drawer
嗯
来开始。
All right. Okay. Okay.
Okay. Do you realize something？这个 chapter 的 study guide 比较长，比较多东西，对吗？
Yeah.
我是特地的，因为我觉得你已经是可以很 focus 了，and and how do I why you are able to focus so much compared to maybe 1 or 2 months ago, or maybe before that, is because you have an anchoring point, right? Whenever that you read something, you have an anchoring point. The anchoring point is the drawers.
Yeah.
Then yes, when you have the intention that there is something that you anchor on, and there's an intention for you to get new information out of this, or to see whether there's new information or new knowledge, 自然自己那个 flying brain problem 就没有了。flying brain problem 一没有的话，你就很 focus 了。所以不管你是多少个 word 少或是多，或者是多 detail，你都可以 focus，right？ So
Yeah.
it's about the intention, right?
Yeah, the
Let's
drawers are
continue.
very helpful because usually, like, when I study, I read like one page, I'm like, okay, I'm gonna take a break now. But like for brain drawer,
Oi.
it's like it's very useful.
Yes, because you have a target, you have a focus point, you have an
Mm,
anchoring point to anchor on,
it's very
right?
effective.
Right. That's good. Come, let's go to third drawer.
Gas pressure, the U pipe with the water and mercury. Mm.
Yep.
Okay. Okay.
Okay, let's go to drawer 4.
Pascal.
Yes,
Ash.
Pascal.
Multiplier.
The strong papa.
Yeah, strong papa. The hydraulic system one. Okay.
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 Okay. Drawer 5. The
Archimedes.
Archie. Archie
Achu.
on
The
Shen.
Shen face. I think Ashin will be sneezing at her home. Like she's wondering why someone keeps on calling her name.
We'll ask her later.
Oh, marine engineering. Okay. All right.
Okay. Last drawer. Bernoulli.
Bernoulli. Benny.
Yes.
It fly to the sky.
Yep.
Oh. Okay.
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 We only took about 1 hour. And I
Ooh.
think you already have a very uh, clear understanding about what is the content of this chapter,
Yeah.
right? So let's continue
The
the
quiz.
quiz. Right, the
Yeah.
quiz, you know the drill.
Mm-hmm.
Read and tell yourself which drawer, and then form your own answer before you read the answer.
All right. Okay, the dam. This one's obviously the first one. Kappa dive into Mercury, pulled by gravity. Let's see. Continue its base. Water shoots out at high speed. Dam. Because the base fluid pressure increased with depth. Mm-hmm. And then high pressure at bottom will force the water to go up. So the pressure difference will be greater. I think, yeah.
Let's see the answer.
H2O. I was like, oh yeah, water shoot out at high speed. Raise the high pressure to faster water flow for the turbines for hydroelectric generation. Okay.
Okay, I think this part is new information
You know, it
for
did
the
mention like turbines once, but it didn't say like hydroelectric generation.
yeah. Okay, that's good. Number
Three
two.
factors. Three factors that are. Oh, is this the formula? Is it the? I think it's the formula. HPG. I think. H depth. P is density and G is the gravity. Yeah, the actual pressure. Okay, let's see. Oh yeah, it is the formula. Okay.
Yep. And this is not P, this is rho,
Yeah,
RHO.
H rho G.
Yes, okay, it's good, but looks like P, yeah. Okay,
Oh,
number three.
14 barrel. Oh, this one's the second one. The barometers. HAPA breathe oxygen. That one. Yeah.
Okay,
The one has mercury. I know one has mercury, the other doesn't. One's like more effective. Other one not. Okay, let's see. 14 barometer was using height of mercury. Yeah, mercury. And then the other one expand. Yeah, no mercury. Less accurate. Yeah. Okay.
okay, let's go to four.
Oh, diver. This one is still the second one. This one's the deep sea decompression sickness. The nitrogen. Too much nitrogen. Let's see. Divergence quickly. Dissolve nitrogen from gas bubble. Rock decompression sickness. Yeah. Pain teaching. Oh, okay. So this ascend slowly. Decompression stop. Nitrogen escape gradually through breathing. Okay. Oh, this one need to count, I think. Okay, ventilation height difference of 20 cm. This one's the formula. This one's the gas pressure formula. H plus P equals the rho atmosphere. Yeah. Justify your answer. So, okay. Gas pressure is greater than atmosphere. Oh, okay. Formula size push down. Excess additional pressure equal to height difference. Okay, okay. Just gas pressure exceeds the atmosphere pressure by 20 cm. Alright.
Okay.
Oh, Pascal principle. The fourth drawer. Yeah, multiplier.
Yep.
Let's use hydraulic system for the hydraulic jacks and the hydraulic brakes. It's from the input force of the small area, and then since it's equal pressure, it'll make like cross multiplication. That's like a multiplication glitch. Let's see. Pascal principle equals undiminished in all directions. Okay. Hydraulic system, small input force. Yeah, equal pressure throughout fluid. Larger position A2, proportional greater force multiplication. Okay.
Yeah.
Hydraulic jet. Oh, why is it usually oil based? I'm pretty sure I did something like this before for like one of the exams.
Okay.
Hydraulic jet. Remember? Yeah, it was because it does not. Yeah. Velocity, low stability. Order, vaporize, freeze. Okay.
Okay.
Hmm.
Number 8. Okay.
Oh, Archimedes. This one is the Shenshin one.
Yes.
This one is because buoyant same as the displaced. Whatever weight of water, it's directly. Oh my god, proportional. Yeah. Okay. Submarine. Oh, submarine. Oil. Yeah, they had ballast tanks. Controls how they float up and down. They put out the air for the pressure so that the weight is smaller than the pressure so they can float up. If the weight is same as the pressure, then it's balanced. And if the weight is bigger than the force, then it goes downward, it sinks. Okay. Allowing water to enter ballast tank, total weight so that, yeah, okay. Right. Displays force, displays fluid. Okay. Oh, this one's the last one.
Yep.
Find the Bernoulli's principle or the aerofoil of the wing combined with Bernoulli's generates lift force. This is because the air will move faster on the top. The velocity of the air is faster there, so it's lower pressure. At the bottom, the velocity of the air is lesser degrees, so it's higher pressure. And it's also the angle of attack and the lift force. Okay. Move the curve on the top, feather bottom. Yeah. Move faster over the curve. Yeah, it's faster on the top because the velocity of the air is higher and the lower pressure. At the bottom, the velocity of air is lesser, and so it's higher pressure. Yeah. Move faster air goes on lower pressure, so air at high pressure. Yeah, upward lift force. Okay.
Okay, let's go to step 6. Let's see whether you can hear the
All right, today we're
Yeah, I
tackling
can hear.
can hear. Okay, let's do it. 8 minutes.
something you can't see, but it's everywhere. It's this invisible force that shapes literally everything, from the deepest oceans right up to the sky. Let's get into it. I mean, have you ever really stopped to think about this? How does a massive steel ship, something that should sink like a rock, just float? Or how does a 500-ton airplane even get off the ground? And get this, how can your foot, with just a little push, stop a 2-ton car? It sounds kind of crazy, right? Like it shouldn't work. But what if I told you there's one single, elegant answer that explains all of it? Yep, the answer to all of these wild questions is pressure. It's this unsung hero, this invisible force behind some of the coolest things in engineering and in nature. And today, we're going to pull back the curtain and see exactly how it works. All right, first things first, we're going to break down what pressure really is. We'll look at it from the bottom of the sea to the very top of the atmosphere. You ever see a big dam? You know how they're always way, way thicker at the bottom than at the top? Well, there's a really good reason for that. It's because of water pressure. All that water is heavy, and the deeper you go, the more weight is pushing down on you. So that base has to be super strong to hold it all back. Okay, so let's get into the nitty-gritty. Liquid pressure is basically the force that a column of liquid pushes down with. And there's this neat little formula for it. P equals H times rho times G. Now don't worry, it's simpler than it looks. H is just the depth, rho is the density of the liquid, and G is gravity. And what's super cool about this is that it means the shape of the container or how much water there is in total, none of that matters. All that counts is how deep you are. Now, here's a wild thought. Right now, you and we're living at the bottom of a giant ocean of air. Seriously, the air above us has weight, and it's pushing down on us all of the time. That's atmospheric pressure. And just like with water, the deeper you are in this air ocean, so the closer you are to sea level, the more pressure there is. That's exactly why climbers on a high mountain say the air feels thin. There's just less of that air ocean pressing down on them. Then, of course, we've got gas pressure. This is what happens when you trap a gas in something, like the air in your car tire. You've got billions and billions of tiny air molecules all whizzing around, bouncing off the inside walls of the tire. All those tiny collisions add up to a big push, and that's the pressure that keeps your tire firm. So let's do a quick compare and contrast. For liquids, it's all about depth. For the atmosphere, it's altitude. And for a gas in a container, it's about volume and temperature. A diver, a mountain climber, a car tire, 3 totally different situations, but they're all about the same core idea, pressure. Okay, so now we know what pressure is. But the really cool part is what we can do with it. This is where we see how a tiny push can turn into a massive force. So here's the big idea, called Pascal's principle. Imagine you've got some liquid trapped in a sealed system, right? If you push on it in one spot, that pressure doesn't just stay there. It gets transmitted everywhere inside that container, uniformly, instantly. It doesn't lose any strength. It's like a perfect message delivery system for force. And this is how we put that principle to work in a hydraulic system. It's really clever. First, you apply a small force to a small piston. That creates pressure in the flood. Then, because of Pascal's principle, that same pressure travels all the way to a much larger piston. And when that same pressure acts on a bigger area, well, you get a much, much bigger force coming out the other end. That's right, it's a force multiplier. Look at this simple formula. It tells the whole story. The pressure on one side equals the pressure on the other. So if you make the output piston, say, 10 times bigger than the input piston, you get 10 times the force back out. It's not magic, it's just physics, but it sure feels like it. And this isn't some abstract science problem. This is happening every single time you drive your car. When you hit the brakes, your foot is that small force on the small piston. The hydraulic system then multiplies that little push into a massive force powerful enough to stop a heavy car in its tracks. And just like that, we've answered one of our big questions from the beginning. All right, so pressure can multiply force. Pretty cool. But what about making things float? Let's dive into the science of what makes things sink or swim. Let me throw a little puzzle your way. Imagine you have a lump of plasticine. You roll it into a ball, drop it in water, and it sinks straight to the bottom. But then you take that exact same lump of plasticine and shape it into a little boat. Now it floats. It's the same weight, the same material. So what's going on? Why does shape matter so much? The answer, my friends, comes from a genius named Archimedes. His principle is this. When you put something in a fluid, the fluid pushes back up on it. We call this the buoyant force. And here's the kicker. The size of that upward push is exactly equal to the weight of the fluid that the object moved out of the way. So that boat shape, by spreading out, pushes aside a lot more water, which means it gets a much stronger upward push. Okay, so let's go back to that giant steel ship. Let's say it weighs 50,000 tons. That's a mind-boggling amount of weight, all of it wanting to pull that ship straight down to the ocean floor. But because of its giant, hollow hull, it also pushes an incredible amount of water out of the way. And if you were to weigh all that displaced water, guess what it would weigh? You got it. Exactly 50,000 tons. And all of that weight creates an upward buoyant force. So you've got 50,000 tons of ship pushing down and 50,000 tons of buoyant force pushing up. It's a perfect balance. The forces cancel each other out, and that's why a massive hunk of steel can just sit there, floating peacefully on the water. Okay, so we've stopped a car. We've floated a ship. What's left? Oh, right, conquering the sky. Let's tackle our final mystery. How in the world does a 500-ton airplane fly? You can actually try this one at home. Grab a strip of paper, hold it right under your mouth, and blow a fast stream of air over the top of it. Now, what do you think should happen? Your gut probably says the air will push it down, but try it. The paper actually lifts up, defying gravity. So what's happening here? This little trick is all thanks to Bernoulli's principle. And it's a bit of a weird one, but it's absolutely key. It says that the faster a fluid, and remember, air is a fluid, is moving, the lower its pressure is. So fast-moving fluid means low pressure. That fast air you blew over the paper created a pocket of low pressure right above it. And an airplane wing is basically just a giant, very cleverly designed version of that piece of paper. You see how it's curved on top? That shape forces the air flowing over the top to travel a longer distance, so it has to speed up. Faster air on top means lower pressure on top. The air under the wing is moving slower, so it has higher pressure. And what happens when you have high pressure below and low pressure above? You get an upward push, a really, really powerful one, and we call that lift. So there you have it, floating, flying, braking, all explained by this one invisible force. Once you start looking for it, you'll see it everywhere, from how you drink with a straw to the weather forecast. So my question to you is, now that you know the secret, where else are you going to spot the power of pressure at work today? Think about it. Thanks for tuning in.
Hey,
All right.
it's getting clearer and clearer, right?
Mm-hmm.
So let's go to the podcast.
Okay.
Welcome back to the deep dive. Today, we're looking at six really foundational concepts that govern how fluids work.
We are, from the deepest parts of the ocean all the way up into the sky.
We're talking liquid pressure, atmospheric pressure, gas pressure, Pascal's principle, Archimedes, and of course, Bernoulli's principle.
Our whole mission here is to just quickly connect these ideas for you. And to start, you really have to grasp the basic difference between pressure in a liquid, which, is mostly incompressible, and in a gas, which isn't.
Okay, so let's unpack that. Liquid pressure. Honestly, it's a terrifying concept when you think about it.
It is.
It's all about depth, density, and gravity. So the deeper you go, the pressure just ramps up incredibly fast.
And that ramp up is, well, it's brutal. Just think of a deep sea vehicle, like the limiting factor.
Yeah.
It dives to 11,000 meters. The pressure down there is over 1,000 times what we feel right now at sea level.
1,000.
And this isn't some niche submarine science. It's the exact reason a simple dam has to be built so much thicker at its base. It's all about fighting that crushing force of the water above.
That's the force of water below us. But then there's the force of the air above us. atmospheric pressure, the weight of the entire sky, basically.
Right, the whole column of air pressing down. But what's so fascinating is that we don't feel crushed, you know?
Why is that?
Our internal body pressure just balances it out perfectly, but if you change your altitude, that balance becomes critical. Go to the top of Mount Kinabalu, for example.
Right.
The atmospheric pressure up there is only about 60% of what it is at sea level, and that drop directly impacts how your body absorbs oxygen.
So you have these massive ambient forces,
Yeah.
oceans, the atmosphere. But what about measuring pressure in, say, a closed system,
Yeah.
like a tire?
That brings us to gas pressure. We typically measure that with something like a manometer, and usually it's measured relative to that atmospheric pressure we were just talking about.
And controlling that localized pressure leads right into Pascal's principle, doesn't it?
It does. It's a perfect transition. Pascal's principle says that if you apply pressure to a fluid in a closed container, that pressure is transmitted equally everywhere.
It sounds a bit academic, but this is where humans get to, like cheat and gain superhuman strength.
Exactly. This is hydraulic systems. Your car's brakes, a hydraulic jack in a garage.
Right.
You push with a small force on a small piston, and that pressure travels through the fluid to a much larger piston.
And you get this huge multiplication of force on the other side, an engineered shortcut to a massive mechanical advantage.
Now let's switch gears a bit to Archimedes' principle. This is all about buoyancy, and it answers that classic question: how does a giant steel ship actually float?
I mean, it feels like it should just sink instantly.
It should, but the buoyant force pushing up on it is equal to the weight of the water it displaces.
So the ship just sinks in the water until it's pushed aside a volume of water that weighs exactly the same as the ship itself.
Precisely. And engineers use this all the time. Think about a submarine. It uses ballast tanks to take in or push out water.
So it's actively changing its own weight to control how much water it needs to displace to go up or down.
Exactly. And that brings us to our final one, Bernoulli's principle. This is about flow. High speed means low pressure, and low speed means high pressure.
And this is where it all comes together for aviation. This is how planes fly, right?
This is the absolute basis for it. The shape of a wing, the aerofoil, is specifically designed to make air travel faster over the top surface than the bottom.
So faster air on top means lower pressure on top.
And that pressure difference between the top and the bottom creates an upward force.
Lift. The force that overcomes gravity and keeps a massive airplane in the sky.
That's lift.
So what does this all mean when you put it together? We've just run through 6 principles that explain everything from dams to airplanes.
And they're all interlinked. So here's a final thought. We've mastered engineering for these extreme high-pressure environments, like with those deep-sea vehicles. We can build things to withstand those crushing forces.
Right.
Given that, could that same technology, that understanding of pressure, truly inspire us to build, say, permanent, stable cities under the sea in the future? Is that actually on the table?
That's a truly provocative thought to end on. Keep an eye out for how these forces shape the world around you.
Okay,
Okay.
deep sea city.
Atlantis.
OK Atlantis 对，好，last step 就是step 8就是这个 story，我们都已经讲了刚才的 story，就是爸爸 dive 进去 Mercury，
Mercury，然后 pull
然
by
后 pull by
gravity，
gravity，爸爸在
can't breathe
ocean，
oxygen，
yes，
然后跟着 ocean，
对，然后
blow 那个 U fight with water 和 Mercury，
OK，
爸爸 strong with 那个 force multiplier。
yes，
I sneeze water out and splash it on Shen's face。
这个我不知道画的听清楚吗？这个是一个杯，然后这个是那个杯的那个 handler， 然后你气，然后那个 coffee splash 去他脸然后这个
You
你跑
run
很
so
快，
fast you fly to the sky。
对，好，现在几点？11:16，我们放下11:16，11:16。哦，才刚刚多了，就是差不多还少过1个小时半。好，我们其实是8:15开始哦，我们3个小时就 cover 了两个 chapter。OK， 然后这2个 chapter 是 quite intense 的哦。然后我可以找那个 book 出来 ，chapter 2是吗 方法这通跑去哪里？这，诶，说明很快结束。E4 C2。诶，没有在我这个电脑，可能在另外一个电脑。不过我觉得你是拿100分的啦。OK，这样，你还有哪一个讲？我先 stop 在这个 record，等一下，考虑。